Hello everyone. In this video, we're gonna cover section 8.2. Actually, just continue with section 8.2 because it's very important you understand how Ito's formula work. Now, we did a few examples last time, so we're gonna do a couple more until this is clear. Now, before we talk about the formula, let's talk about the chain rule in calculus. So recall this from calculus. So in calculus 1, so this is from calculus. Actually, this is, let's say, I think this is in calculus 3. So let's say that z is a function that depends in two variables, t and y of t, where clearly y depends also in t. And here there is no randomness at all. This is just calculus 3. Remember, if you want to take the derivative with respect to t, this will be the partial derivative of f with respect to t times dt plus the partial derivative of f with respect to y times dy dt. And then if you want to write it in differential form, then the z, notice here that these cancel each other out. You'll end up with the partial of f with respect to t dt plus the partial of f with respect to y dy, because the dt's will cancel. And notice the similarity between this part and this. It's exactly the same thing, even though this is random and this is not random. But notice that this one has an extra derivative. And as I mentioned before, this had to do with the quadratic variation of the Ito process or the stochastic process. But just to refresh your memory, you remember the Taylor polynomials or Taylor series, which is one of the most useful things in mathematics. You learned this in calculus 2. So this is one of the main topics in calculus 2. There you have a function can be written in terms of a series like this. This is actually from 0, and this is the n derivative evaluated at some constant a to the n power over n factorial. But remember, you can use any value you want from the expansion, and usually from there, a very common way to write this, especially like in numerical analysis, is this. If we use this formula and expand around delta x, this will be the same thing as f of x plus f prime of x delta x plus f prime of delta x times delta x squared. Actually, this should be f prime of x, so this should be just x over 2. This should be f double prime, and then this keeps going. So from here, if you solve for f prime of x, which is this one, so you want to solve for prime of x, notice that this will be equals to f of x plus delta x minus f of x. We're just moving this to the other side. and then you divide by delta x, and that will be minus f double prime evaluated of x times delta x over 2, and so forth, or plus or minus this. Notice that if you take the limit, which is the definition, f prime of x is the limit as delta x goes to 0 of all of this. Now this is the thing that is very important, that it doesn't happen in the stochastic calculus. The limit of this, as this goes to infinity, as delta x goes to 0, all of this goes to 0. So this part, all of this goes to 0. So it disappears. Well, that's not the case with Brownian motion. So this part is still here, which is technically would be like this part. Here you can see the second derivative. So the point is, if the variable is non-random, this thing goes to 0. This is the reason why. But in a stochastic variable, that doesn't happen. That's why we end up with this extra term. All right, so now let's try a couple examples and see how this works. You're gonna have to find the derivative using Ito's formula in the next test at least once, and in the final for sure. This is one of the most important things in this class, to know how to use Ito's formula. All right, here consider this example. Let y of t be the Ito process or stochastic process defined by t squared wq t, where remember wt is the winner process, which remember the wt minus w0 has a normal distribution with mean 0 and variance t. All right, so here usually the most important thing to do when you trying to use Ito's formula is to identify the correct function for g. So here gt of x is just technically t squared. You can say x cubed. All right, so we need the partial derivative of g with respect to t. That will give you 2t x cubed. Then we need the partial derivative of g with respect to x. Remember, x is just the Brownian motion, so this will be equals to 3t squared times x squared. And then we also need the second derivative of g with respect to t, or partial derivative, so this will be 6t squared x. Then if we plug it into the function, so from here dy t is going to be the partial of g with respect to t, which is this. Just remember, once you plug it into the formula, x is represented by the winner process, so this will be technically just 2t w q t, and remember all of this is multiplied by dt plus the partial derivative with respect to x, which is 3t squared w squared times dw t. This is actually, yeah, dwt plus 1/2 the second derivative. Well, the second derivative is 6t squared w t times dt square, actually dwt square, but remember that dwt square is equals to just dt. In general, remember that dt times dwt is equals to 0. dwt times dt is also equals to 0. dt times dt is also equals to 0. Only dwt times dwt is equals to dt. Finally, just combine the like terms. So we're going to have dt. You have dt in here. Oops, not that. You have dt in here and also here. So therefore that should give you a 2t wqt plus 3t squared wt, and then plus 3t squared w squared t dwt, and that's it. Now you can write the dt in front if you want. So instead of having it there, you can write it on the front, but either case is fine. So you can write the dt here, and that's it. All right, let's look to the next example, which it doesn't look like you had to use Ito's formula at all, but you will see right now that it's going to be fundamental to solving this problem. You also have to use the result of other homework problems to do this one. So we'll try to do everything at once here. All right, so here let's say that we have the function gt of x is just equals x to the 4. Technically, we have a process which we could say yt is equals to the Wiener process to the 4 power. Okay. So then the partial derivative of g with respect to t clearly is 0. The partial derivative of g with respect to x is going to be 4x cubed. And the second partial derivative with respect to x is going to be 12x squared. All right, so then from here, we have the derivative of y, but remember that y is just this. You'll see in 1 second why I'm writing like this. If you use Ito's formula, so by Ito's formula, this is equals to 0 times dt plus 4 wqt dwt plus 1/2 times 12 w squared dwt squared, which is just equals to 4 wqt dwt plus 6 w squared t dt. So remember, this part is just equals to dt. Therefore, from here, remember that if you integrate both sides, the integral will cancel the derivative. So therefore, if we integrate both sides, we will end up with w t to the 4 power. This will equals to 4, the integral from 0 to t, wq s dws, plus 6, the integral from 0 to t, w squared s ds, where, remember, this is the stochastic integral or the E2 integral, and this is this part is the regular integral, even though this is random. Oh, by the way, in the original question, this should be lowercase t, not uppercase t. So just make sure to fix that part. All right, so next we take the expected value in both sides. Why? Because you have expected value here. You can see that this is technically what you want in there. So the expected value of wt to the 4th power will be the same thing as the expected value of this plus 6 the expected value of this to be s ds. All right, so this is w squared s ds, and this is pretty much what you want this. All right, notice that this is equals to 0. Why? Make sure that you check this part. It's very important that this is equals to 0. So therefore, what we have from here is the integral from the expected value of the integral from 0 to t of w squared s ds, which is what you want, is going to be equals to 1/6 times the expected value of w to the 4th power, which technically this is the 4th moment of wt. Remember that wt minus w0 is a normal distribution 0t. So all you need to do is figure out this part, which is, I think, is homework 12, but we'll go over this quickly right now. All right, so we have from the last page, the expected value from 0 to t of w squared s ds, that this is equals to 1/6 the expected value of wt to the 4th power. Well, remember, this is the 4th moment. Now, we have used this formula many times. Since wt, I just mentioned too, that is normal 0t, the moment generating function phi of lambda, so this is the moment generating function, is given by this. This is e to the lambda square t squared over t. You even have this on the test to show that this was the case. Now, to find the moments, in case you forget this, you take the derivative of this with respect to lambda. If you want the first moment, you do the first derivative. You want the second moment, you do the second derivative, and so forth. For example, the first moment, it will be e to the lambda squared t over 2 times times, since you're doing with respect to lambda, this will be 2 lambda over lambda is just lambda t. Then if you plug the derivative, which in this case it will be f prime of 0, that will give you 0, which implies that the expected value of wt is equals to 0, which we already knew. Now you do the second derivative of this, and then you evaluate it equals to 0. And again, this is just basic calculus. You should check this. Then you end up with t, which, remember, this is the expected value of wt squared, which is the same thing as the the variance, which we know from here that is equals to t. So if you keep taking the derivatives using the product rule, it shows that the fourth derivative, this evaluated at 0, is actually equals to 3t squared. Again, you should definitely check this, and this is also part of the homework as far as I know. So therefore this is actually equals to then 1/6 times 3t over 2, which will give you 1/2 t squared. And that's the answer to that. Now, the last thing we will do is go back to Ito's formula, but now in 2 dimensions. You can do it in multiple dimensions, but we only will do 1 and 2 dimensions. So if you haven't still fallen in love with Ito's formula, this will be the time for that. So now instead of having only one variable, you have 2 besides t. Now if you look to a Taylor series in 2 variables, which again, if you're going to study math, especially applied math, this is one of the best tools to know, Taylor series in more than one dimension. So then you're going to have g of t plus delta t. This will be the expansion. X plus delta x. And then this will give you g of t of x plus the partial of g with respect to t dt, the partial of g with respect to x dx, and then the 1/2, the second partial of g with respect to x squared, delta x squared, and so forth. Again, in regular calculus, this will disappear, but in stochastic calculus, that will not disappear, because for something like this, in stochastic calculus, you will have something like this. You will have wt plus delta t minus wt, which remember this has a normal distribution, and therefore this will not go to 0. So in regular calculus, this will go away, but in stochastic calculus, it won't go away. So therefore, Ito's formula in 2 dimensions, so Ito's formula in 2 dimensions is the following. So notice now how you have t, x of t, and c of t, where the x is equals to this, and the c of t should be the same thing. You can change this to another, it's mu1, the same thing in there. This will be c of t. Then say sigma 2, and then dwt. Now here things can get a lot more confusing and more messy if these two are different Brownian motions. Here we assume it's the same Brownian motion, because you can have 2 different ones. You can have 2 that are independent or 2 that are correlated, and that will get too messy. For the rest of the class, we only assume you have 1 Brownian motion that is shared with the two variables. So then, if we do the derivatives in 2 dimensions, you end up with this beautiful thing right here. All right, so let's do an example to see how this works. So let's say that you have a function y is equals to x times z, where x is a random process and so is z. Actually, each of them should have their own differential, stochastic differential equation. So therefore the x, let's say, is equals to a dt plus b dw t, and then let's say that the z is equals to c dt plus e dwt also. Now here the function g of t, now x and z, is just going to be equals to x and z. Alright, so we need the following derivatives. The partial of g with respect to t clearly is equals to 0. The partial of g with respect to x is just equals to z. The partial of g with respect to z is equals to just x. The second partial of g with respect to x is going to be 0. The second partial of g with respect to z is also equals to 0. But the partial of g, the second partial of g, which is respect to x first, and then respect to z, equals to 1. So therefore the dy, for now, this will be 0 dt plus z dx plus x dz plus 1/2 times 0 dxt square plus 1/2 times 0 dzt square, and then plus 1 times the x times the z. So it should be the z. So this is what we have so far. The dy t is equals to z dx t plus x dz plus 1 dx dz. But remember that dx was equals to a dt plus b dw t. Okay, so this was equals to this. And then dz was equals to c dt plus e dw t. And then for this one, well, you had to multiply then in this triview, so it will be times c dt plus e dw t. All right, so let's focus on this part first. Remember that dt times dt is equals to 0, and dwt times dwt was equals to dt. And whenever you multiply dwt times dt is also equals to 0. So if you multiply this times that, you will end up with 0. This times that, you will end up with also 0. This times that is also 0. The only thing that survives is this times that, which will give you be times dt. So then what we have is technically this. You have za dt plus z vdwt plus zx dt plus ex dwt plus b times e times dt. Now you have dt in here, in here, and in here. So you can combine all of those. So if we do that, you will have az plus zx plus be dt plus, you can combine the dwt, so this will be zb plus ex dwt, and that's it. It's the end of the story.